Hello.
Oh,
Hey,
now
Stephanie.
I'm unmuted. Hey, good to see you.
Yeah,
Thanks for organizing.
pleasure. Sorry it didn't work with getting you in there. It seems like it's a bug in the system that you always start as an attendee, and we have to promote you to panelist.
Interesting. But you used my like Kerberos _ email or
Yeah.
okay.
Yeah. The MIT email that I got from the emails that you sent me, I guess. Is it underscore? I actually don't know. It comes up with Stephanie.
So my email is actually a mailing list because my correct email address is super bad. It's like Mueller with an underscore at the end, and it just goes to people's spam folders. So I use like Stephanie.Mueller, but that's not my Kerberos. So maybe that messed up the Zoom login, you know. Okay, but the screen sharing also works. That's good.
Yeah, I can see that.
Super. Yay.
Fantastic. I saw the chameleon. That was awesome.
Yes. How are you doing? It's snowing, right? And you're living a little outside. Are you snowed in or?
I'll see if I can turn the computer on. It's not quite snowed in.
Nice.
So you can see a bit of snow on the trees, and then a bit of wind blowing snow away.
Yeah, we have a lot here. It's like a lot. Oh, I actually still wanted to get my phone. Give me 1 second.
Sure. Tony, how are you?
I'm doing well, Professor.
Cool.
We have about 3 or 4 inches here. It's heavy, wet snow. Shoveling the driveway has been a lot of fun. But my kids are enjoying it. They're just came in and having hot cocoa.
Oh, cool. Did they do snowball fights outside?
It's not the right type of snow. It's kind of just sort of wet and slushy. So they tried, but how are your sons doing?
They're inside right now. They had a costume school day, half a school day today. But they released them early on a different time schedule that they had communicated to us. So the boys were actually standing out in the cold for 20 minutes.
Oh no!
Yeah, so they were a little bit peeved at the time and didn't want to go out anymore.
Here's Cambridge.
Oh wow!
Yeah, it's a lot more, no?
Yeah, it's a lot more. You can almost go skiing.
Yeah, it's very close. Yeah, I was surprised. I thought it would just like drizzle down a bit, but it's actually quite, you know, it's still there. I'm impressed. It still keeps going.
Fantastic. Tony, thanks for sending the announcements to the other departments.
Oh, my pleasure.
Yeah, thanks for that.
Stephanie, are you still going horseback riding? Is that still an option? Or
no, not really. Also, like a lot of the farms have closed. I think there was just, you know, they're always like short on money, and I think the COVID situation didn't help it. So this is not happening at the moment.
They're closed, you mean closed for good, or?
Yeah, I think they just moved further west. So I think around Boston, within like a driving distance of 30 to 40 minutes, there's nothing. It's too expensive, I think, and not enough clientele, I guess. So they just like move further and further towards in country, and then it's just too far for me. It's not worth it anymore. You drive. Then you actually have fun.
That's a pity.
No, tough luck.
Yeah, it's one way if you can call it, but hopefully that's not lasting too much longer.
Yeah, that's very optimistic.
I tend to try to stay on that side. I mean, winter is going to be a bit rougher, and then hopefully by spring or so we'll have a better clear idea of how quickly vaccines can be.
Yeah, I mean, I always just look at how the world is doing, and the world has never gone down, and case counts is only going up. So since the beginning, so I would say we're not even halfway through. You know, if hasn't even peaked yet. So it's going to take a while.
Yeah, I think it depends on how good we are now as a society or as a world to find the right vaccines fast, right? How efficient are these processes and how fair are these processes?
But I'm not sure if you like read the German newspaper. So Germany is like a trustworthy source. So I'm like, okay, if like somebody in Germany said that, it's probably going to be roughly correct. They said even if they have the vaccine, let's say in February or March approved, they will need at least 9 months to deliver doses to all Germans to just be able to manufacture and get it out. And that's just like tiny Germany, you know. So
I can see that, and that makes sense, right? You can't just have it pop up on everybody's desk when it's done, right?
Right.
Don't have these type of technology yet, but I think what a society we can do if we get this right is to figure out who gets it first and on which timeline, right? That we are realistic about it. And I think you take account on who is essential in keeping society running as it is, right? And not sort of screwing up as we tend to do at the moment. And then you prioritize people, not by money, but by some measure of agreement of everybody. People are important, right?
Can I ask you before we keep chatting, how does this webinar stuff work? So you see the people in the attendee list and then you take the questions from the chat box and you ask me for them, or how do you do it?
So we sometimes play it by ear, but the idea is that before you start your talk, I'll remind people that we have the Q&A and that they can put questions in the Q&A throughout the talk, so they don't have to keep them in their head and forget them.
Yeah.
And then at the end of the talk, we can pick from there. And often, depending on the number of questions, I would say we'll take the time to unmute the person and to ask the question in person, so you have a voice with it, and you can actually have maybe even a small discussion depending on how many questions you have. And
you want to do questions at the end, right? Because otherwise you have to like panelist the person or something so that they can ask, or?
Well, if you say I'd rather want to sort of do questions in the middle, we can also do that, right? Then we can go by the Q&A.
Yeah, actually, I think that's better, because otherwise, you know, I always feel like if somebody talks for like 40 minutes straight, it's a lot of listening. So if you feel like you're okay with this, we can actually do the question whenever they come up. I think that's better than, yeah, I mean, depends if there are, but you know, I think if there's a question every few slides or so, I would also be happy to just take.
So do you want to interrupt? Do you want me to interrupt you, or are you monitoring the Q&A yourself? And
no, you could be like, you know, I will try to make some pauses from here and there, and maybe you can be like, hey, Stephanie, there was this question from so-and-so on blah, blah, blah. What do you think, or whatever? I mean, if you feel it's a good moment, if you feel like it's just like not the right question for this moment, then you can just let it go.
So I get the power of triaging. Yeah, no, I can do that. So I'll try to see if either you give me an info question or interrupt you politely.
Sounds good.
That might depend on the complexity of the question, but I could still ask the person to ask it themselves, or I could just paraphrase it.
I don't know. I've never managed. I've been in one of these webinars before, just as like somebody doing like Q&A for some industry thing. But I don't know how much clicking that is to be able to allow somebody to ask their own question.
There's a little bit of mechanics involved. It's not that bad. It depends on the amount of time, right? If you push up, so we start 5 after the introduction, and then talks are 40-45 minutes to leave some time for the questions at the end. If you do questions in the middle, we can actually go into this time of the questions at the end a little bit, right?
Yeah, and you know, I'm flexible. I have like, you know, 4 topic areas I would like to cover, but if you run out of time, I just cover 3. So, you know,
I was about to say, the biggest risk is that you don't get to the stuff that you want to get to.
Now that's at the front, you know, of course.
Good planning. Good planning. Question from Zahil, who asked about whether these aminos are accessible online, and we do put them on MechE YouTube channels, or on the MechE YouTube channel. We have one, but we have to transcribe and everything, and that takes a bit of time.
Yeah.
we're still in the process of getting the first ones ready. And then actually on a note, I'll probably run it by you so that you can look at any sort of questions in the description that might come up.
Sounds good.
So this is a question to all attendees who are here at the moment. We still wait for a couple of minutes to make sure that everybody can come in. We have the 5 minutes after MIT sort of timeline. But at the moment, Stephanie can only see me. And I can smile a lot, but maybe she wants to see a couple other friendly faces. So if any one of you is happy to be on the panel, to smile at her, to look curious, to look inquisitive, just put it in the chat. I can promote you to panelists. There's an attendee who has already raised their hands. Jaya, perfect. I assume that
you can
means...
also promote Deshita for me.
Cool.
And Martin.
Ah, fantastic. Hello, Jaya.
Hello.
And Martin, you said?
Yeah.
Are they going to ask you cheeky questions, or are they going to be...
No, they are my PhD students sneaking in.
Good. Fantastic. Now you need a couple of people who would ask cheeky questions to balance. So people are coming in. Hello, everyone. Thanks for joining us. We still wait a couple of minutes because we want to give people a chance to come into our virtual seminar room here. We pile them in, they take their seats, and then we get started in a few minutes.
Hey, Jaya. Thanks for volunteering.
Yeah, this is something that is a dimension that sometimes misses, or sometimes it always misses in Zoom meetings, right? If you don't see people and you just look at your screen in an auditorium, in a lecture hall, it's so important to read the crowd and to see where you are.
Yeah, I find it even harder when you do the screen sharing, right? Because now you have this conflict of how many people do you want to see versus how much screen space is this taking up on your slide, right? That's a hard one. I struggle with this like all the time. I'm always like, where am I going to put the people?
Yeah. Well, that phase into a discussion as to when can we go back to a different way of more personal interactions. And I hope we will soon.
Yeah, very soon, hopefully.
Okay, forward 2. I have a couple of things to say about you. That's always fun. And maybe I get you to blush.
What? Then, no way.
No,
no German joke.
I won't play a funny joke on you this time. But I'll hand it over to you at about 4 or 5.
Yeah,
that actually means
that's good.
I have to get started.
So wait, so people they don't see you right now? You have like a button where you can be like, I want to be seen right now, or I don't want to be? Or?
I actually don't know that. I don't have that view. I think they probably see all of us, but when you start to talk, what the audience is going to see is your slides when you put the slides on, and they're going to see you, not the rest of the panel.
Sounds good. Okay, interesting.
Well, I'll try this actually right now. I share the screen with the announcement about you, and then I can get started. So there's the announcement of Stephanie. So hello, everyone. Thank you for joining us this afternoon for this exciting MechE colloquium. We have a few of them going through the season into winter, and hopefully that's a highlight of your week. And we definitely have a highlight today with Stephanie Müller. I should say Professor Stephanie Müller with the full title. She is an ex-Vendo Consortium Career Development Assistant Professor. That's a long title, all deserved, in Electrical Engineering at MIT and in Mechanical Engineering at MIT. And Stephanie is also a faculty member in CSAIL. And that fits in terms of her work, CSAIL, the Computer Science and Artificial Intelligence Laboratory. And Stephanie is the head of the Human Computer Interactions Engineering Group. I got this right?
Yes,
the
that
HCI
sounds good, yes.
The work that she's doing is really awesome. She's shaping the physical world around us by using computation paradigms and sort of using the evolution of computing to shape objects around us. this is pretty easy now in the digital world. I guess you guys use SolidWorks. Some of you might use Blender to create artistic renderings, or also Minecraft to have fun with it. But in the physical world, that's not quite as easy. And as I see Stephanie's work, she is actually showing us how it can be done. She shows us how colors can change an object. She shows us how objects can shape or how they can self-deploy, and also how you can match a complex electronic circuit to an object's geometry, or how your couch can do math puzzles for you. And these type of things are really amazing, but she puts it in the context of tools that we might be able to use it at some point. So she fashions these tools for the group at the moment, and hopefully all of us can get access to these tools and work with them to shape our world around us. And that is really sort of a game between the wants and the needs of the user, us if you want, and the constraints in the physical world. And Stephanie and her group are really creative about sort of reconciling the issues and the advantages there. This has been very well recognized by a lot of people around the world. Stephanie is a Forbes 30 under 30s in science fellow. That's an elusive crowd. And she also has an
under 30, you know.
Yeah, but you still you made that. You made that accolade. And an NSF Career Award is something that you can count your own. Also a Sloan Fellowship and a Microsoft Research Faculty Fellowship. And these are certainly high sort of recognition of the amazing work that you and your group are doing. So Stephanie, thanks for joining us. And I'll give you the word in 5 seconds. The only other thing that I have to do is remind the audience that we have a question and answer section that you can put questions in at any point in time. You can also use the chat. I'll monitor both. And Stephanie has agreed to answer questions throughout the talk. So we will pick the questions as they come, and then I'll try to phase them in at the right moment in time. And maybe I even ask a couple of people to ask their question in person. Stephanie, thanks for being with us today.
All right, thank you so much, Matthias, for the excellent introductions. It was super detailed, and I'm really glad that you already know so much about my work. That really makes me, feel happy. All right, can you see my screen? So good? Okay, awesome. All right, thank you so much, everybody, for coming. Just before you was going to start, I'm super glad to talk to you today about the fantastic research that my research group has been doing. So all the credit goes to my PhD students and postdocs for all the projects I'm showing today. And I'm just going to summarize our work on advancing personal fabrication, making physical objects as reprogrammable as digital data. So it's basically bringing the physical world and the digital world closer together, as Matthias already introduced. All right, so if you actually think like 50, 60 years back in computing and you compare this to today, I'm sure we all agree that computing really has revolutionized how we process and we interact with digital data today. And I'm sure if you think of your own personal favorite application that computing has enabled, you will have your own example. But because I'm in 3D printing and 3D modeling, my favorite example will come from product design. So for instance, if you think about how somebody would have designed hours and hours doing this on a piece of paper to make the design, and then if, let's say, they wanted to change the color of the car or something else about the car, they would have to spend like more hours redrawing everything to show the new design to somebody. So today, now that's actually super easy, right? You just open your 3D editor, you load a 3D model of, let's say, a digital car, you apply a new color in seconds, and you just push the button and it's right there. So however, these capabilities that we have for computing today, they really cannot yet be applied to physical matter. So if you fancy like a new color for your car, for instance, well, that's going to be expensive and time consuming, right? So you have to go to like a shop and then somebody's going to spray your car from front to end. Definitely taking probably like a day, it has to dry and so on. And then you are going to have spent a lot of money on it as well. So in my group, we're actually asking ourselves a bunch of questions around how can we change how we interact with physical objects so we can actually manipulate them as easily as digital data. And I want to show you 4 different projects on this today, and I will start with reprogrammable appearances. So on reprogrammable appearances, we just had 2 papers in the last 2 years. If you are interested, you can read the details there, and I'm going to give you a short overview in the next 10 minutes. So we developed this smart material that you can spray onto an object, And then you can simply project a light pattern onto this object and you can change the object's appearance. This is fully reprogrammable. So if you want to change your object, you can apply a new color pattern and update it right away. Since we just spray our smart material, you can also spray it on, let's say, a phone casing, and on a daily basis, you can have a new design on your phone. We can spray it onto textiles. So this is a collaboration we have with New Balance at the moment, checking out how you can have different clothing and pairs of shoes on a daily basis. And you can also apply this to cars. So maybe in the future, when you have car sharing, you don't actually have to take the car as it is. You can customize it to your liking, which may even increase like the amount of car sharing people are happy to do. All right, so I just want to show you a few more examples before I go into the technical details. So here you see 3 of these phone cases, one you saw in the video, and reprogramming them takes about 20 to 40 minutes at the moment. So you could really do this on a daily basis, or even, you know, after a few hours if you want to design, iterate on a product. These are 2 shoes, again, like roughly 45 minutes, because that's more of a 3D geometry on the side there. And then the car was also about like 20 to 30 minutes. This is a collaboration we have with Ford Automotive at the moment. So we're imagining this like more like a washing machine, like a projection system moving by, recoloring the car, and you have the new appearance. We also have like more upcoming collaborations on textiles. So you could imagine, rather than having like 20 times a shirt in different colors, maybe just have a white shirt and you can recolor it. And we also are starting a collaboration with Benjamin Moore on wall paints. So you could imagine you paint this on your living room wall, and then on a daily basis, you come from the office, you select a new appearance, and your entire room is going to change, you know, to whatever mood you're in for the evening. So how does it work, right? That's of course the question. Is it magic? No, it's not magic. It's actually, once you understand how it works, actually pretty straightforward. So we use these materials, they are called photochromic dyes, and by default they are transparent. Now, when you shine some UV light on them, they actually switch from transparent to being colored. Now you can use them in your normal environment, so the color maintains. And then you can shine visible light on it from like an office projector, the same you would normally use to project my slides, just not today since we are in a Zoom call. And it switches back to transparent. So here you see this one more time as a summary. So to saturate from transparent to colored, you use UV light, and to desaturate, you use like visible light from an office projector. And you can do this in a loop as many times as you want. So there's a big limitation when you actually buy these materials from a vendor, they only exist in a single color. So you can buy transparent to cyan, or you can buy transparent to magenta, or transparent to yellow. But obviously that really limits you in the type of colors you can make. So you could make any level of cyan, but not a multicolor thing, for instance. So how do we achieve these multicolors that I showed you in the previous examples? So here's the idea. We mix all the 3 colors together. So we take cyan, we take magenta, and we take yellow, and you mix it all together, you get black. And that is actually consistent with the CMY color model as you would expect it from normal 2D printing. Again, these are just like photochromic dyes, so it's a special material. So and now what we have to do is, so we basically have this mixture bottle where everything's mixed together, which gives you black. And then what we want to do is we want to deactivate either the cyan in the bottle, or we want to deactivate either the magenta in the bottle or the yellow to create all of these different colors you see on the right side. So right side again shows you the same bottle, just like with different deactivation levels of these 3 color channels. So now you may ask, like, okay, sounds good, but how do you actually make, let's say, the cyan in the black bottle transparent? Like, how would you do that? And the trick, yeah, what you have to know here is that each of these dyes in the bottle have a different absorption spectra of light. So this is pretty complicated here. You see at the bottom of this chart the wavelength at which they get transparent. And then the y-axis just shows you how much light they absorb at that wavelength. So how quickly would they desaturate at that wavelength. And let's say you wanted to make the cyan transparent. What you actually need is you need a light source, let's say roughly here, where the cyan would get transparent, but the magenta not quite yet. So for the magenta and the yellow, there's not a perfect solution, but you would basically, again, need like a different light source at a different wavelength to make the magenta transparent. And then you need a third light source to make the yellow transparent. So where do you get these light sources from? Well, I already mentioned we use just the office projector. If you actually open up an office projector, like the one on the right side, you actually see they have 3 different light sources. They have a red LED inside, a green LED, and a blue LED. And now the red LED, luckily, is exactly where we need the wavelength to be to deactivate the cyan. And the green is where we want to have it to deactivate the magenta, and then the blue can deactivate the yellow. So what you basically have to do is, in our algorithm, we just project a lot of, let's say, red light, blue light, green light at each pixel until we are at the right saturation level of the cyan, magenta, yellow to achieve a specific target color. So you see, for instance, let me replay this. So you see, for instance, in the middle, it will be finished first, because going from a fully saturated black to a dark blue goes pretty quickly. You only have to make a little bit transparent, right? But if you have a yellow or something, you actually have to make all the other stuff transparent, which takes a bit more time for the projector to shine. And as Matthias said, if you have any questions, you can just post them in the chat, and I allowed Matthias to interrupt me anytime if somebody has a question.
There's one.
Yes, super good. Yeah.
This is David Andrew Cricks. How quickly does the ink fade in typical light you'd encounter day to day?
Yeah, so that's an excellent question. So if you obviously use a visible light for the activation, they also fade under daily light after some time. So we did some experiments indoors. So indoors, I think I don't have the chart here, it's in the paper, but I think the cyan and the magenta last, I think like 12 to 16 hours or something, gone a little quicker. So it's gone after, I think, 6 to 8 hours. What I want to say for this is we also got some new photochromic dyes in the last months. And for instance, that yellow that we just got already lasts for 2 to 3 days. So from my side, it's like, I'm a computer scientist with like MechE background as well. And for me, it's like we did everything we could from a systems building perspective, and now it's up to the material scientist to develop better photochromic dyes for our use cases. Yeah, and then the other part is we don't think of the system as something that you do once and then you just use your one texture for a month, because it's something we can already do today. So we actually envision this as really changing how people interact with their products in the daily life, right? So you change it every couple of hours. Maybe you come in with like black shoes to the office, and then you go in the evening to a party. So you recolor your shoe, make it more colorful, you go there. So it's much more of a quick update use case.
David, thanks for the first question. That actually broke the ground for 3 more that we have at the moment. Stephanie, how many would you allow before you want to go on?
Yeah, I'm happy to have like 1 or 2 more questions.
All right. The first one was, and this is probably a short answer, but does it apply to texture or color alone? And this is from Lois Amelia Wampler.
Can you say one more time?
Does it apply to texture or color alone? So can you only change the color, or could you change the texture?
Fantastic question. I love this. So we only looked at color so far, but I would love to look at texture as well. I actually did a few experiments like a few years ago with something called like swell paper that is used for like visually impaired people that like swells when you expose it to like some heat. So if you could combine that, maybe like you can change the color and the surface structure with like a special paper underneath, that would be cool. But right now it's just color.
And then there's a question here about, can you model the desaturation process to control the duration of light for each part of the image? Or can you do it through some form of closed loop control? And that would be Samuel Gollop who asked the question.
Yeah, that's actually a fantastic question for transitioning into the next section. So right now we pre-computed, we don't have a closed loop, but it would actually be great, if the texture desaturates over time because of some external light, it would actually be great if you could put it back in the system and check which color it currently is and then update based on that. That's fantastic. All right, so let me tell you a little bit about the algorithm actually underlying this, color change. And I just told you, I know it's pretty complex, but I hope you remember, I told you you take like the red, green, and blue light, and that deactivates the different color channels in the bottle. The correct question then, of course, is how long do we actually have to shine this light, right? Do we have to shine it for 5 minutes or for 1 minute or for how long actually? Right? So we ran a bunch of experiments. We actually sprayed each photochromic color separately on a sample. So we had a cyan sample, magenta sample, yellow sample. And then we exposed it to all of the projector lights. We shown the red light from the projector, the green light, and the blue light on each of these samples. And then we took some pictures and we measured how quickly do they actually desaturate and become transparent. So here you can, for instance, see that if you shine red light from the projector, you just make a red PowerPoint slide, you project it onto the bottle, you would see that cyan and magenta desaturate after, what is this, like 1,800 seconds. I can't do the math right now. I think it's 30 minutes or something. And then the yellow would actually not be affected. So the yellow would stay there and would stay saturated. And that's actually, if you look again at the wavelengths, it's very consistent, right? Because the red light really is on the far right of the wavelength spectrum. So the cyan and the magenta go away, but the yellow is not affected. The yellow stays. So we did this for all the different colors, and then you know how long everything takes to disappear. And then we use this in optimization. I spare you the details. It's basically a simple optimization that looks at, if we have our current color, which is black, we always start from black, how long do I have to shine red light, green light, blue light, given these data charts I have shown you to get to the target color. And then with like fancy math, this looks like this. So the bottom line there basically says if X is your current color, so again, X is black. If I now shine red light for a certain time frame, if I shine green light for a certain time frame, and blue light, what would my color be as a result? And then we try to minimize the error between this estimated color and our color we actually want, and try to get this towards 0 to have the closest match as the outcome. Again, if you're interested in those details, there's more on it in the paper. So how do we prepare the materials? It's actually pretty straightforward. So we buy these photochromic dyes from a company in Japan. So you get these little bottles with powder. And then we bought, just for us, like automotive lacquer as the carrier, and we just mix it into this lacquer. So you see this here. This is just a lacquer from the hardware store. Then we put in our dye. We mix this on a mixer. We do this for cyan separately, then for magenta separately, and for yellow separately. And then after we mix them, this is just a short demo for you that you can see it actually works. And then we mix them in a specific ratio to each other to make sure we get the closest approximation for like high saturation. And then after you mix that as well, you can spray it onto your object. So what's next? So this is, working pretty well, but there's obviously always stuff you can make better. Right? So I showed you how, we get a little closer to making the hard physical problem not quite as hard anymore. So if you compare the right image to our small demo here of being able to recolor the car, it's not instant as in digital, but I think this example here was like 20 to 30 minutes or something like this. Let me see, it's 40 minutes for both sides and 20 minutes for one side. Okay, so what can we make better? So the dyes, as somebody already asked the question, dyes is a big problem for us, even just getting the right colors. So we actually need a cyan, magenta, yellow. You can't get that at the moment, right? You can only get like a blue, which is not quite right. The yellow actually looks pretty good. And then the magenta is also not quite right. So that by itself already limits the colors you can get in the end because you don't get the pure colors. But there's actually research in the space in material science. And we reached out to somebody who has a cyan dye. He's also in Japan, and he actually sent us like a tiny 1 gram sample from his research. So we were able to give it a shot, but it was not enough to spray onto all of the different objects.
I have 2 questions here.
Yeah.
Should I ask them now or should I hold up?
Yeah, I'm happy to.
Actually, I can bring a couple of people in. I'll ask Sayed if he wants to talk, and then George also has a question. Sayed, do you want to ask a question yourself or should I ask it for you? That didn't quite work.
Too many
so
technology issues.
Yeah. He said, please ask it for me. Okay. What are the advantages of your technique over electroluminescent paints, like the one by Lumidor?
Yeah,
So
that's an excellent question as well. So I've actually shown a project in a little bit that also uses the electroluminescent paints. So my group's actually pretty aware of this technology. I think what is really awesome about the photochromic dyes is they don't glow, right? They really look natural. When you actually hold it up, it looks like you just painted on it, versus the electroluminescence, it's much more like a display. And there's also technology, I'm sure you're aware of this, called electrochromic, that is actually not glowing. It looks much more like the photochromic dyes, but they are only single color. So they're just like blue. I think they exist in like orange, but they don't exist in like high resolution multicolor like we showed it, at least as far as I'm aware of it.
Thank you, Stephanie. And George has a question. Professor George Babistatis.
Yeah, hi, Stephanie. Good to see you
Hi,
again.
good to see you.
This is fascinating stuff. So I was wondering, this optimization that you showed for the color selection, is that convex? And why are you using L2? For example, if you used a different metric, L1 or something else, might it result in sort of different color hues or something that may be visually more striking or maybe visually more dull? I don't know.
So George, this is like an absolute great question. So I'm not the super optimization expert, I have to say. So my postdoc implemented the optimization, so I'm not sure like what the benefits are of different methods, but I would love to talk more. And I think there's a lot more that could be done in optimizing the overall color gamut. And you're probably right, if we did this in like a smarter way, we could probably squeeze out even more from the color space. I would love to talk more after this.
Sure, yeah, that'd be fun. Thanks.
Super, thank you, George. I keep going?
Yeah,
sounds good. Okay, great. Okay, so I talked about like better colors would be nice, right? Faster would be nice. We just did a few early tests. So if you actually double the light intensity, it also goes like a lot faster. So I'm not sure what the dyes can take. Maybe we burn them out if we just blow more light on them. But I still have this like little dream that maybe in the future it's going to be just a few seconds rather than like 20 minutes or something like that. Then we also just bought a UV projector instead of a UV light. So if you just use a UV light, you just blow and you saturate everything and everything becomes black. If you use a UV projector, you can actually per pixel saturate. And because the saturation is so much faster than the desaturation, we can now actually make these grayscale textures here in just under a minute, which, again, gets me closer to my dream of real time. And then this is a collaboration we just started with a FOA, that's a textile institute here on campus. Our current platform. Can you still hear me? On the left side, you see our current platform. So we have the visible light projector and the UV light stand there. But if you think about, you want to make like maybe a t-shirt that you can recolor, you would have to like, turn around in front of the projector. That's maybe not so cool. So the idea here is, can we get rid of the stuff and we put the light source directly inside a fiber? So as I said, like the visible light projector has RGB inside. So we just put RGB LEDs in the fiber, and there's the UV light. So we put a UV LED in the fiber. And now if you weave this, can we just have like clothing that can recolor itself without any external projection system? So Afoa already has these types of fibers, and we are just like starting to spray our photochromic coating on this. Cool, and then this is the last project I want to show in this space. This is for 3D printing. So right now, if you use a resin 3D printer or you use something with a filament roll, you're typically limited to one color because you can only pour in one resin in the tank, or you can only mount like 1 or 2 filament rolls. So our goal here is to actually mix our photochromic material into the resin or into the filament roll, and then be able to have a multicolor 3D print just out of the box with a single material. So this is a prototype system we are currently working on. You see on the right side with the 2 projectors and the flipping mirror that goes between curing and coloring, curing and coloring.
Stephanie,
yeah.
When you optimize the colors, do you do it for sort of a quantity in the spectrum, or do you do it on the human vision, on human perception?
That's also an excellent question. Yeah, excellent question. Right now, we just minimize it based on the CMY distance in the computer. It's not based on perception. That's the short answer. It would be much better to optimize based on perception, that's for sure. Yeah, that would be great. If somebody has, wants to collaborate on this, please reach out. Okay, let me keep moving. So with the photochromic material, that's kind of cool, but you have to reprogram all the time. So we also had like one project where we asked ourselves, can we have multiple appearances without the need to apply light or apply electricity just on its own? And for this, we got inspired by something that's called lenticular lenses. And I'm sure you have seen these. I actually can show this maybe here first, this little video. Oops. You know, when you have like birthday cards, right? You look from two different perspectives, you see two different images, and there's no need to like, you know, reprogram something on a complicated way. So basically, if you look from this angle, you would see like this portion under the lens. So you see, let's say, red. If you look from another angle, you see another portion under the lens. So you see blue. So this exists in 2D, but not yet for 3D objects. And I actually think it would be super exciting to have this for 3D objects, because let's imagine I'm at home. I'm actually super annoyed at the moment because I have work and relaxation life in the same room. Let's say, could I not just like sit at my office desk, but I would not see the couch because I don't want to get distracted? And could I, for instance, sit on the couch, but I don't see the office desk, because if I sit at this angle, maybe the desk disappears from where I'm looking at. So could we imagine like these kind of, you know, angle-based rooms where you only see what's good for you in that current situation? So we implemented something for like 3D objects that can compute these appearances from different angles, and I will show you a few examples of this. So of course, 3D printing can't make like tables and couches yet. So all of our application examples are small, but I hope they can give you like the idea. So for instance, we made this position guiding tools where, let's say, you're doing an exercise with a, how's it called, like a handlebar, a dumbbell, right? And you don't know at which angle you should hold it. But if you actually 3D print the lenticular lenses on it, it can actually show you, let's say, a check mark once you hold it at the correct angle to your eyes. So you know, yay, I'm in the right position. For minimalist product design, this would be interesting. So let's say all of our products right now have like tons and tons of text on the back, which really destroys how products look like. Could we, for instance, build products in a way that when you look from the front, you only see the beauty of the product, but if you look from the side, you see the instructions because you're looking at it from a different angle. This is an example where, let's say, you drop something and normally you would not see it. You drop your AirPod case from your, headphones. Can we print lenticular lenses around them so that when you drop it, it actually is going to flicker because the angle to your eye is going to change as something falls to the floor. So I hope you can see this here. It goes from like green to black as you change the angle to your eye. And then this is a last example I just want to show. This is for like personal messages for cheering you up. Yeah, we are all a bit sad about being at home today. So in this like slipper example, you don't see anything from the side, so other people don't see anything. But if you actually look down, you see like a cheer up message just for you to feel more happy. So what do we actually need to be able to make these lenticular objects? Okay, first we need a 3D printer that can actually print this. And this is something that just made enough progress in the last years. We need a 3D printer that can print lenses with optical clear material. The printer needs to be able to print full color patterns. And the printer obviously also needs to be able to print the rest of the object geometry. So we are using this Stratasys 3D printer here. And then we have our own computational conversion pipeline that I will show you right now. So I will walk you through step by step, so it's not going to get too complicated. So this is our 3D editor that we built. You can first position cameras where you want to have different viewpoints, and then you load in textures you want to see from each viewpoint. So you can say, I want to see up the chair up from here, but I don't want to see anything from there. Then after that, our conversion pipeline distributes lenses over the geometry and makes sure everything is nicely packed and positioned at optimal placement. And then our pipeline computes based on the angles you defined which color has to be under the lens at which position. So that when you look from here, you see the green. When you look from there, you see the red, for instance. So first, we take all the input textures you loaded and we map them under the lenses. So we just say like, okay, if this pixel is here, it belongs to lens number 45, for instance. Then we average the color under each lens. And then we still have to distribute the color under each individual lens to make sure you see it from the correct angle. Yeah, and once you have this, you just get 2 fabrication files from us, one for the color texture and one for the object geometry and lenses. And then you can like print it out on the Stratasys 3D printer. And once you print it, you take it out from the fabrication bed. And then in this case, this is the top of the slipper, and we just attach it to the bottom, and then you're like ready to experience the different appearances from different angles. So we also did a lot of testing because, you know, printing lenses is not super straightforward at the moment. So we tested a lot, like which sizes are actually realistic and what are the color resolutions we can do on these 3D printers, because that also has an impact on how many appearances do you actually see, or do you just see like a stop motion movie from left to right. There's also a lot of ideas how we can make this better. So printing lenses on objects, as I said, is right now is not super nice because then your object surface is like bumpy with all the lens surfaces. But we have some ideas on how we may even be able to use like a smooth surface and like redirect some of the light so that you see the right appearance from the right angle. Okie doke. So if there are no questions, I will just keep moving. So we looked at the appearance, and I also want to talk about how we can actually bring sensing capabilities to objects. So appearance is nice, right? But we also want to have user input so we can actually sense what is the person doing. And for integrating more sensing into the environments, we actually started looking at sprayable user interfaces. So you use like a spray can and you spray functional inks. So you can see this in action. So we have loaded a conductive copper ink into a spray can. And now you can just like spray this onto a wall, for instance. And you have like a functional slider right there. Now here we are spraying a visual design on top of it. So you can actually cover up all the conductive traces with a nice design. And now you're ready to like interact with your user interface right after you finish spraying. So we have this electroluminescent touch button for turning on the lights. And then here you can set the brightness with the slider. And you can also set the color with the other slider that we just sprayed. And that's actually a technology that works so well. We just did it in my class in the fall with like 40 students, and they all sprayed their own interactive elements. So it's really encouraging that, you know, people can actually do this and they can augment, you know, large scale entire rooms and furniture. So for the example you just saw, we use copper ink, which you can use for like touch button sliders, wires, connectors to the microcontroller. But you saw like if you have copper ink, you will always visually see it. So you have to like overspray it. But there's also a conductive material that's called P.PSS, which is actually transparent. Now, if you have this transparent material, let's say you want to augment your furniture, for instance, you can just like spray it on. So here we spray 2 touch buttons on the couch. And these are some projected guidance stencils we give to the user that they know where to spray. And now your couch has these sensors integrated. And you can actually build like full user interfaces. So here we can sense, is the user sitting or not? And then let's say if the user is sitting, we load this photo album application, and we can also sense, you know, hover and touch on the couch itself. So here if the user is swiping left or right, we change the photo. So this is a pretty straightforward, you know, bringing the digital world to the physical world by just like spraying this material in a few minutes onto a piece of furniture or a wall, and you have like full interactivity right there. Of course, you know, in my group, when we have a project, we always have a design environment with it. So here, this is the environment we built where you can lay out your touch buttons and sliders. And once you're done with your design, we generate stencils for you, either for laser cutting and then you spray, or for a projector, so you actually know where you're spraying on the object and you're not spraying all over the place. Okay. So there's a lot of these sprayable inks. So I just showed you like 2 conductive inks, but there are also display inks. So this is how we sprayed this electroluminescent display I showed you. And again, this is probably too much to like fully understand how this works. but you literally just have to layer these 4 materials and you have something that will, glow like a display. So you can see this here. We spray copper first to make the display. Then we spray a dielectric material for insulation. We spray the phosphor. And then because this is a little bigger, we spray a copper bus around it to distribute the current. And then we spray a final clear conductor on top. So the phosphor is sandwiched between 2 electrodes. And you're done with your display. And now, you could just like use it in your application example. All right. So we did a lot of testing with the spraying. It's actually really versatile if you want to augment different types of surfaces. Yeah, so you may say like, okay, that's funny that you sprayed on like sponge and marble and so on, but we were really curious, can we augment like really crazy surfaces that you can normally not augment if you use a different technology? And because spraying is non-contact, like all of the particles actually really distribute nicely on the structure and you get these like clear conductive traces. So here's the conductivity or the resistance measurements you can see is highly conductive. And here this is just showing what I just said, where this is a porous stone and the conductive particles really like go into the little cracks and form like one nice conductive surface, which you would normally not have if you use something else. All right, so I showed a lot of like augmenting surfaces and changing appearances, but I think a big part of bringing digital and physical closer together is also making sure that all the editing environments that we use today keep track of what's happening in physical when we design in digital. So I want to show you a few projects in that space. So there's a paradigm in user interfaces that is called WYSIWYG. It's like what you see is what you get. And this actually enabled a lot of people to participate in computing. So if you think back, this was mainly about rather than programming something on the computer, you would actually be able to just like have a visual user interface where you can drag together a web page really quickly rather than writing some JavaScript code, for instance. And how would the same principle look like for like physical modeling of objects? So it's actually very interesting if you think about how we make or plan and design our objects today. There's not a lot of knowledge in the 3D modeling process so far. So let's say if you want to design something for laser cutting, you're making your cool model, you design everything, and then you're like, oh man, I don't even have enough material to make this, or I really wanted to make this from this material, but now I'm running out. That's not great. So we also looked into how can we actually, preview some of these fabrication constraints in the editing environment already so you can make more informed design decisions. So here's the paper if you're interested. I will show you a short summary. So you see our editing environment like on the left side, where basically during the design, we already show you how much material do you have left on each material sheet for laser cutting. Here's a short video of this. So when you design, you directly, rather than selecting from colors like blue, green, red, you actually select from a material palette. So you say like, this should be green cardstock. And then on the right side, the moment you draw your shape, it immediately positions it onto the sheet. So you see here, Tisha, one of my PhD students, is drawing like a few more shapes and they immediately get placed onto this green cardboard stack on the right side. And the system then can also give you warnings. For instance, here she wants to make a second tree and she's running out of this orange cardstock and it's saying like, hey, by the way, if you wanted to make this, either you need to order more or you need to make this smaller because otherwise it just doesn't fit. And it also tells you, hey, if you're interested in other orange materials or other red materials, how about you try this other substitute that could also work for your use case. So you may be interested, like, how do we actually keep track of what you have available? So there's two options. Option number one, every time you actually laser cut something, the laser cutter knows that it just cut out the shape from the sheet. So you can actually save that path in your material database. So we always know if you loaded a fresh sheet and you cut out these 3 cutting jobs, how much is left, right? Because we have that information. And the second option is if you just come from a different fab lab and you bring your own sheet, you can also take a photo, and then that photo gets fed into our material database. And again, based on that photo, we can extract what it was already cut, and we can then recommend you where to place it. So I showed you this for, ooh, I'm running out of material, but there are a lot more issues in fabrication, right? So more issues, same story. This is one example here. When you want to, for instance, engrave on existing objects, you design something in laser cutting. Let's say you want to engrave it on this phone case, and now you're like really stuck there with, you know, like what material is this I'm actually engraving on? I'm not sure because I just bought this from somewhere and it didn't come with a detailed description of what it is. And then how should I actually split my design? Where exactly is that line? So that's like super complicated, right? So we had a project that can help with this, and I will show it here. So we built a novel sensing technique inside of laser cutters. And you can basically say, here's my design, please scan this for me. And then our sensing will trace the path, and it can actually detect at each position which material is this made from. So the way we sense this is something called Speckle Sensing. So Speckle Sensing, I know it's a lot of info today. I hope I still have you. With like Speckle Sensing, you just use some light from a visible laser that hits the surface structure of the material, and then this laser light bounces off. And if you use a camera, you can actually see this like speckle pattern that looks different for each material. So the bottom line here is we are not looking at color or anything, because if you just looked at color, right, you just see like black with a camera. Now you don't really know, is this black leather or is this like, you know, some black plastic? It's really hard to see in a camera image. But because we look at surface structure, it's actually much easier to say, you know, there's a difference between cast acrylic and Delrin, which is actually really hard to see, again, with just like a camera image. So we actually went to like an electron microscope and we took like pictures of each of these samples, and we were like, yeah, the speckle image is actually right, you know, because all of these structures are different. You can't see it with the human eye, you can't see it with a camera, but surface structure is different for each material. So yeah, so this basically allows us, let's say you have these like 6 very similarly looking material sheets here for a camera. But we can actually say this one is acrylic, this one is Delrin, right? By just like looking at the surface structure with our speckle sensing technique. And again, a normal camera would just say this is white, you know, and wouldn't be able to say what material it is exactly. And helpful for laser cutting actually just happened in my class. Like a student wanted to cut something that was dangerous, but with speckle sensing, we can tell you, you should not cut this material. There are toxic fumes, don't do it. Okay. Great, and I will just like, I think show 2 more projects and then I will wrap it up. There's also issues with electronic design tools. So if you think about it, how like most electronic design tools still work today, you do your 3D modeling here, you do your electronic design over there, and they don't really want to be together and give you like a super good preview of what you will get. There's stuff like Altium Designer, but it still requires you to edit your board in a separate window and things like this. So we were like, can we make a more integrated design?
Stephanie, should I hold the questions to the end?
You can go for it. If it's for the previous project, maybe I just answer them now. Yeah.
All right. So Professor Neville Hogan actually asked, could you apply speckle sensing to discriminate types of biological tissue?
Oh. So that sounds super interesting to me. I would love to learn more. I think it all comes down to, does your do different biological tissues, and I'm not sure which tissues you're working on, have different surface structures. If they do have different surface structures, that should be possible.
Cool. And then Professor Gary McKinley here asks, can you sense glass and distinguish it from acrylic versus Lexan, say?
So we haven't tried glass, we have tried Lexan versus acrylic. So as long as the surface structure is different, I'm not sure how much glass surface structure is different from acrylic, but I don't want to say yes. I think my bottom line is if it's different surface structures, it will work. So Lexan versus acrylic, we tested. Glass we didn't test, because glass you can't laser cut on like these commercial laser cutters, but would be great to give it a shot.
And then I have another question from David Griggs. Does the Specul match rely more on external texture than internal material? Or as in, would you cast 2 acrylic blades from different companies with different final finishes, perhaps confuse the matching? Or do all producers of a certain material come close enough to avoid problems? So I guess external versus internal scattering is an interesting question here.
Yeah, I'm not sure about the scattering. That's a fantastic question. We tried like a bunch of different companies for the cast acrylic. So they all were like, let's say, sufficiently similar that from our machine learning algorithm that we used, they still fell into the same confidence category, because the other materials are just way more different than what like maybe a small manufacturing difference would cause.
And George has a question that he could actually ask himself if you want to, George. Otherwise, I'll ask it for you.
I was just wondering if you could make. I may be making an illegal suggestion here, and we're being recorded. But I was wondering if you could forge currency this way. You could make like a surface that today it appears like a dollar bill, tomorrow it appears like a euro, and you know, the $100 bill. Nowadays, it has a security feature that is very distinct. It has sort of a 3-dimensional motion effect. I wonder if it is possible to forge that as well.
That is a very interesting area for research. I totally agree. Like on a slightly different note, like the student who's working on the store, he also suggested, you know, maybe we can engrave like teeny tiny micro cracks in the surface that can then also be used as some sort of like tag you can detect with the Speckle Sensing. That's again like not visible to the human, right? So it would be kind of like a security feature in that sense as well.
Right.
So it's very interesting.
If that works out, you will not have to write any more proposals, right?
Just get the money myself. Sounds good.
Thank
People
you,
in the chat are really picking up on the ideas, George. I think you're planting a seed here.
Okay, awesome. Thank you for the question.
There's a number of other questions that sort of spread across the topics. I don't know how you want to play this, because you have a couple of things that you also want to discuss still. Should I hold the question quick, and then we...
Yeah, how about I spend like 2 minutes to show the last 2 projects real quick, and then maybe we can wrap it up there, and whoever wants to stay around can stay around. Okay, I just want to quickly show the electronics tool we built. So our tool allows you to like really design electronic function and 3D model prototype in one environment. So here you can place all sorts of like electronic components. And then because we actually start with sensor modules as input that we download from SparkFun or Adafruit, like all the logic connections are also maintained. So basically, as you move stuff around, all connections are still there. And then once you're happy with it, you can draw your actual physical wires. So you can do your routing, right? And then at the very end, you just select the entire area and you say, I want to fabricate this. And this creates like a 2D projection on the side. And you could either send this to like a flex PCB manufacturing facility, or in our case, we use something called conductive inkjet printing, where you take a normal 2D printer and you fill silver ink in it, and you could just like print out the circuit. And then my student has like a cool fabrication pipeline where first he applies like normal tape, because that's going to go on the object. And then he has like pre-made footprints for the different electronic components, and he just like solders everything together. I'll let the video play for a second. So he's just putting on all the small components on the corresponding footprints. Then he's going to apply, this is conductive double-sided tape, so that when he actually cuts out these little component footprints and sticks them on the circuit, there's immediately electrical connection. So now he's going to stick them on. All right. And then once you have them on, you can just like, you know, after you put all your sensors and electronic components on, you just cut it out. And because in the first step we applied this like double-sided tape at the back, you can just like take this off. And here we made like a soldering iron with a little smoke detection module, so it tells like the student like don't inhale too much. It's kind of like a quick way to make physical prototypes where everything is combined. So you have a few more examples just to show you how we can merge to make like one integrated prototype. Okay, and then I'm just going to show one more project for the last part, and then I'm going to wrap this up. So we also thought about, I showed you a lot of projects of people making stuff from scratch, but if you actually look at it, most people today, they just download things, right? They download images, they download music, they download videos. So maybe not everybody wants to make stuff from scratch. They just want to reuse. So we were asking, is there a way for people to just download a physical object that's fully functional and just have it made and you don't have to do anything about it? And that's right now not really possible with like electronic component fabrication in one process. So we actually had the idea, how about we build such a machine where you can maybe just download a quadcopter and the quadcopter will fly off the platform immediately after you downloaded it. And that needs a lot of different things. You need to make geometry, traces, place components, solder. And I'm just going to show you a video of how we make this with our new fabrication process. So yeah, we enhance a laser cutter with this add-on you see on the left side there, and I will show you the steps right now. So this is a close-up view. I know it's hard to see. It's inside the laser cutter. It's cutting the outline of the quadcopter right now. Then our add-on has a silver extrusion. So it's just putting down the electric traces. So our add-on also has a pick and place. So you can actually pick components from the side of the laser cutter. We have like a little storage box with different types of things. Here in this case, we are picking the quadcopters and the main microcontroller for the running the code. And then we actually use the heat of the laser itself to cure the trace. So before this like laser curing, your trace is not conductive, but the moment we apply this heat with the laser, now everything is soldered. And once our laser add-on is done with its job, you can see the LED will come on and blink, so the device is fully functional right away. And then in a second, I hope the rotors will start and it's going to fly off. Whoop. Okay, here we go. All right, so yeah, there's a lot more I could tell you about like what we can do with like, the laser soldering and the trace making and how awesome like Martin, who did all this work on this project, implemented the pick and place. But I just want to show you, we can now basically download and make something end to end that can work right off the fabrication bed. Okay, since I want to give some time for like questions, I just want to zoom out. So my lab really works on everything, bringing physical, digital together in all sorts of different, hopefully interesting ways for you. And I showed you 4 different things: programmable appearance, then seamless integration of sensing with objects. I showed you editing environments that combine physical and digital. And then I also showed you how we can actually fabricate functional objects by just like downloading them and having them made on our prototype platform. And with this, I want to thank all of my awesome students who are doing all the hard work on this and all of our sponsors. And with this, I will wrap it up. And if there's any more questions and anybody wants to stick around, I'm happy to take them.
Stephanie, thank you. This was fantastic. There are a few questions, and we can also promote anybody to panels now that you can speak with Stephanie a bit more. It figured out quite well the last couple of times that people hang out afterwards and speak a little bit in person. So let's start with the questions. And we have one question from Lois, and I just have to find Lois here. Maybe we can unmute her and you can ask the question yourself.
Hi, I had a question about your copper spraying. So I wanted to know the feasibility of that for a wide range of things. For example, is there a minimum wire thickness that you were able to achieve? I know that there aren't really wires, but also, are there any like reliability differences that you've seen between a common wire and a spray? And also, are there major differences between current and amperage capacities?
Okay, these are all fantastic questions. So yes, it does make a difference how thick you spray the wire. I don't remember like what's the minimum requirement. I'm sure it's in the paper somewhere. There is a minimum requirement, that's for sure. So I'm not sure if I can give you the detailed answer for this. I think I was mainly surprised by like how reliable it works on different types of surfaces, which I think is like a difficult thing to achieve with any other technology. Now, if spraying is like the ultimate solution, compared to whatever else your favorite technology is, I think that would need like a more detailed comparison probably. If you want to reach out and tell me like how you would do it otherwise, we can maybe tell you if that's if spraying is better or worse than whatever you're using at the moment.
Awesome, thank you so much. I was just curious from a lot of design standpoints, so that's very helpful. Thank you so much.
Yeah, thank you for asking.
Thank you. And there's a question by Haluk. Haluk, I just promoted you to the talking abilities.
Thank you, Professor. Am I audible?
Yes.
Yeah.
I was really interested by that spray, the sensing spray, the smart spray that you had, and I was wondering if you had thought, or if you could comment on the feasibility of using that for contract tracing, especially in this day and age. If you could comment on that.
Oh.
Thank you.
So that's very interesting point. Maybe you can like elaborate more on how you think about it. I can tell you how I think about it. We actually have like a project in my class right now where people are using like the conductive spray to spray it on different surfaces to see, for instance, how often have people like touched surfaces and which types of surfaces. And then they actually use some of the display paint to display if you should not touch that surface anymore because maybe it has been, you know, interacted with too many times and needs some cleaning. So that's certainly like a possibility to use the spray paint in like a very current up-to-date use case.
Thank you. Thank you.
You get a couple of compliments and a few other questions, or first related compliments. It's really wonderful work. All the best with the next step. That's from Sayed.
So much.
And then Teresa Worth wrote, thanks so much for the talk. It's exciting to think about all the viable applications of this work, both fun and practical. So
yeah, and if anybody
is,
thank you so much. And if anybody's interested in collaborating with us, you know, if you want to send me an email is like on my slide down there. We are always happy to collaborate, especially with like other areas to find new interdisciplinary, you know, work and opportunities.
And there's a question by Professor Garrett McKinley, who should now be able to talk.
Yes, let me just also say wonderful work, really, really creative stuff. And I don't know if you've ever read anything by William Gibson, but a number of his novels actually envision exactly this idea of printing something that
cool.
essentially walks or crawls or flies right off the assembly line. So I rather like that. But I had a technical question about your sprayable copper. I missed the composition of the copper. It's a colloidal copper that's in a volatile solvent, or how do you deliver it? What is it? What's your constraints to make it sprayable?
Yeah, that's a fantastic question, Gareth. So we just buy it. That's unfortunately the bottom line. There's no magic we do. Okay. We just go to a company, it's called Lumidor, and you can actually just buy it off the shelf. So I'm not exactly sure what's in it. I'm sure my postdoc would know, who has played around with these inks, but I'm not exactly sure what's in it. But I'm happy to send you the link if you want to see like how it's composed.
Please do. Yeah. Okay,
super. Thanks for the question.
I think Professor George Barbastalis had another question on the Speckle Sensing. That might be something where you actually have a really good collaboration partner potentially. He also is very interested.
Yeah, I also thought about it. We should work together on some of the optics things.
Yeah, maybe in the interest of Halloween coming up, maybe I'll send you a separate email, Stephanie.
Sounds good.
Great stuff, by the way. Thank you.
Thank you so much, George. See you. Bye-bye.
Perfect. I think, yeah, Stephanie, this is all the questions. Thank you for a wonderful talk. This was amazing. And that means we're officially at the end of the seminar, but if you want to speak to Stephanie a little bit more, hang around. We make everybody a panelist who wants to be a panelist, and then you can talk in very vivid interactions. Thank you all for joining us today.
I also want to wish everybody a wonderful weekend, and thanks so much for coming.
I think, can you hear me? Am I still unmuted?
I hear you. Yes.
Yeah.
Yes, yeah. I unfortunately I have to leave to go to another call. Otherwise, I would stick around and chat. But this was fantastic. I hadn't seen any of these things recently. I would love to get a copy. If you'd send me a copy of the paper about the sprayable copper ink system in particular.
Yes, we do.
Yeah, that's wonderful. I think it's connected to this idea of what's the minimum sprayable line thickness that one can do. You know, it's obviously set somewhat by the size of the particles, but you know, I'm sure it's many times the size of the particle, and just interested in the resolution control that you have there. So
yeah, that sounds good. I took a note. I will send it to you later.
Yeah, yeah, no hurry. Yeah, I'll be in touch. Okay, great talk. Bye.
I think Hillary has a question.
Thank you. Yes, my name is Hillary. I'm a PhD student in MechE, and I work on building more efficient pumps. And one of the things that I'm looking towards in the next few weeks and months is integrating sensors, and particularly I've been thinking about pressure transducers, integrating them into the 3D printed pump casing. So I was particularly interested in the work you presented around being able to disassemble a sensor and put it on a complex surface. And really curious about the software that you all have developed on that, and then also, yeah, kind of the transfer of data in breaking those down.
Great. So I can definitely connect you to my PhD student Juni, who can either give you access to the software or can show you how to extend it, because we have already shared it with somebody else and they were successfully able to use it for their research project. So if you send me an email, I can get you in touch, and maybe you guys can chat a bit on how that could help you for your research project.
Yeah.
How is the data transfer working? So the basic pipeline is we import Eagle files into Rhino 3D, and then our code kind of reads those Eagle files and uses, there's a SparkFun 3D library that reconstructs the Eagle file into a 3D model of a sensor. And then because we read the Eagle file has all of the wire connections already, so we know the logic. So we just maintain everything and then we snap it on the 3D geometry.
Exactly. Wow, that is so cool. Well, your presentation overall was really inspiring, and appreciate your work. So thank you for your input, and I'll certainly follow up.
Yeah, thanks, Hillary. Yeah, if you send the email, that would be great for us to have a new application areas.
Yeah, always interested. Okay, cool.
Bye-bye.
Ernie, really cool.
Sounds good. Okay.
The chameleon is that is just beautiful, and that's close to my heart in terms of the interest that my group has.
Yeah, I know. We should do more together.
Yeah, that would be good. But all the other work is also mind-blowing. It's really fun to see how you use a lot of concepts that are, when you put it in the way how you put it, really intriguing, and you would say, why didn't somebody do this before, right? I think that's a hallmark of a good idea, to just sort of make it work and make it happen, and with a very smart sort of background in the underlying physics and the science, right? I think the Speckle Sensing isn't quite all that straightforward, right? You have to deal with a lot of how would you say, intricacies of this.
Yes. Yeah, I'm always impressed by all my students. 2 of them are still hanging here because everybody has very different skills, right? And it's really, really helpful for me. I learn a ton, from everybody, so that's super helpful.
Cool, fantastic. Thank you. So we have recorded this. I think at this point I can probably stop the recording. And